So, good afternoon, ladies and gentlemen. How are you doing today? My name still remains Banjo Olalekun Peter. So, today I only want to share a brief review on the classification of equilibrium. Classification of equilibrium. When you are classifying equilibrium can be homogeneous equilibria or it can be heterogeneous equilibria. So we can either have one homogeneous equilibria, then we can have heterogeneous equilibria. Now, when we are talking of homogeneous equilibria, it means the species in equilibrium, they are in the same phase. Or in the same state of matter. Your reactant, your product, your catalyst itself, they are in the same physical state of matter. That is homogeneous equilibria. A very good example is like iodine gas reacting with hydrogen gas to form hydrogen iodide gas. As you can have here, hydrogen gas, iodine gas, a reversibility sign, hydrogen iodide gas. Hydrogen is in gaseous form, iodine in gaseous form in this reaction, then hydrogen iodide also in gaseous form. The equation is very balanced. This is homogeneous equilibria. The reactant is in gaseous form, the product is in gaseous form. A good example too is N2O4 in gaseous form to give 2NO2 in gaseous form. You can see our reactant is gas, the product is also gas. So they are in the same state of matter or in the same phase. Then again, if we have the production of ammonia by Haber process, production of ammonia like nitrogen gas reacting with hydrogen gas to give ammonia gas. This reaction has a catalyst, but as it is like this, since the catalyst is not there, it is homogeneous in nature. So when you have your reactant, your product in the same state or in the same phase or the same state of matter, you call it what? Homogeneous equilibria. Although sometimes when catalyst is involved and the catalyst is in different state of matter with the reactant and the product, then it will no longer be homogeneous in nature, but it can be heterogeneous equilibria. So when you have heterogeneous equilibria simply means that the reactant, the product, even the catalyst, they are not in the same phase. If any of the reactants or any of the product or catalyst are not in the same phase or the same state of matter, we can simply call it what? An heterogeneous equilibria. Take for instance, reaction of iron with steam. Now iron reacts with steam at red heat. Reaction is like this, where I have iron is in solid form reacting with steam, H2O in gaseous form, that's 4, to give a product that is like this, because iron will be 3 here, so Fe3O4 in solid form plus hydrogen gas. The hydrogen here is in gaseous form, the steam here is in gaseous form, but the product here, iron here, is in solid form. This product here is in solid form. The reactant iron is in solid form. The product here too in solid form, but the reactant steam is in gaseous form. The product hydrogen is in gaseous form. As long as they are not in the same state of matter, then it is telling us it is an heterogeneous equilibrium. And if we have homogeneous equilibria before, like a reaction of sulfur 4 oxide gas plus oxygen gas, like this now, a reversible reaction, you now have this. This is homogeneous in nature. But by the time I put the catalyst, vanadium 5 oxide, which is not a gas, the vanadium 5 oxide is in another state of matter, but it is not in gaseous form. Be it in solid form, here, it changes this guy from homogeneity to what? Being an heterogeneous equilibrium. Why? Because the catalyst is in different phase or different state of matter with the reactant and the product. Now, we talk about equilibrium constant. Equilibrium constant. I say equilibrium constant, Kc or Kp. Equilibrium constant. But equilibrium constant can be in terms of concentration and it can be in terms of pressure. In the last class, we were able to show relationship that exists between Kp and Kc, because there is a relationship that exists between Kp and Kc. If you could remember in the last video, I said Kp is equals to Kc into bracket RT raised to power change in number of moles. And I told you, by the time change in number of moles is 0, the Kp value and the Kc value become the same thing. But how do we come about writing equilibrium constant? Whether we are writing the equilibrium constant in terms of pressure or we are writing the equilibrium constant in terms of concentration. Okay, we arrive here through what we call the law of mass action. The law of mass action, which states that rate of reaction is directly proportional to the product of the concentration of the reactant or the active mass of the reactant. So if we consider this reaction where A plus B is giving C plus D. So the rate of forward reaction RF can be Kf, concentration of A, concentration of B. That's the rate of forward reaction. If I need to consider the rate of backward reaction, I'll have rate of backward reaction RB is going to be Kb, concentration of the product. And in the last class, one of the conditions for a reaction to be in equilibrium is that the rate of forward reaction and the rate of backward reaction must be the same. So we have RF must be equal to RB. And in that case, we substitute this guy here, this guy here. We have Kf, concentration of A, concentration of B, is equals to Kb, concentration of C, concentration of D. And in that case, we can find the ratio. What's the ratio of Kf over Kb? We have, therefore, Kf over Kb means concentration of C, concentration of D, divided by concentration of A, concentration of B. So this Kf over Kb, Kf over Kb is our equilibrium constant, Kc, which is concentration of what we have at the product side divided by concentration of what we have at the reactant side. So our equilibrium constant of concentration is concentration of the product divided by concentration of the reactant. Thank you.